Let's talk about the first one. This is again a method. It's a technique. Learn the technique so that you are able to solve the questions. The method of substitution. In this method, we will make one of the two variables the subject of the formula, preferably the variable that has a coefficient of 1 or any variable that avoids the use of fractions. I will talk about this in detail when we start working with examples. So let's call this equation 1 and substitute this equation into the other equation. Let's call this equation 2. So you will have two equations. You'll have two unknowns, so therefore we have to require those two equations. In the first equation, we will make one of the two variables the subject of the formula. Right? I will tell you exactly how to make that choice strategically when we work with examples. Right? By doing so, we get rid of one variable and write the other variable in terms of one variable. We simply solve as if we're dealing with linear equations. We then take this value, substitute it back into equation 1. Let's look at a few examples. Now this will be abstract because I wrote it as rules, so let's do an example. Let's say I got 5x minus y is equal to 16 and 4x minus 5y is equal to 9. How many unknowns do I have? I have 1 and 2. So therefore I require two equations. Right, in a practical sense, if you're in the real world, you're trying to solve a problem and you have two unknowns. In your mind, you need to look for two equations so that you'll be able to solve both for both the unknowns. Right? Now, let's look at this. We will rewrite equation 1 in the form so that it can be substituted into equation 2. We choose y since we can avoid the use of fractions. So if I look at equation 1, I want to try to re-express equation 1 and make one of the two variables the subject of the formula. Right? Once I make one of the two variables of the subject of the formula, then what this means is wherever I see y, I can input 5x minus 16. So since I chose equation 1, I'll take equation 1, re-express it so that I have y on one side. So it means wherever I see y, I will substitute it into equation 2. But what this enables me to do is every time I substitute, I get rid of one of the variables. So now what we have an equation that is only in terms of one variable, which is x. So if you have an equation in terms of two variables, then you need two equations to solve. But what our primary aim is to get those two equations to a single equation with one variable. Now, does not look like linear equations, as if we were solving linear equations. A very straightforward example. And therefore we solve, but once we find this x, you take this x and you put it back into the equation that you re-express to find out the equivalent y value, and therefore you solve for the question. Understood? So let's do that. Now, the reason I chose y to be the variable, because if I let x equal to, see 5x is equal to 16 plus y, if I add by y on both sides, therefore x is equal to 16 over 5 plus y over 5, if I divide by 5 throughout. Now we're starting to work with fractions. So that's the reason why I strategically chose y to be the subject of the formula, because it has the coefficient of 1. Therefore, when I let it be the subject of the formula, it enables me to solve the question very simply. Understood? So therefore now I have 4x minus 5y. 4x minus 5 is equal to 9. But wherever I see y, I must put in 5x minus 16. Next rule to remember. Whenever you substitute, you get rid of one variable. We need to do this so that we can solve the question using linear equations. Secondly, whenever you substitute, parenthesize. Very important. Whenever you substitute, parenthesize. Wherever I see y, I'm going to put 5x minus 16. But you must put it in brackets. Why? Because you could have unlike terms and that negative has to distribute to each term in the bracket. So we're utilizing the distributive law that I talked about in algebraic expressions. So therefore we have 4x minus times the plus is a minus, 5 times 5 is 25, 1 times x is x, minus times a minus is a plus, 5 times 16 is 80, which is equal to 9. Therefore, we have 4x minus 25x. You owed someone 25 rand, you paid them 4 rand, so how much do you owe them? You owe them 21 rand. If I subtract by 80 on both sides, I get minus 71. Therefore, x is equal to 71 over 21. Right. Now, what do you do with this x? Remember, you need to find two solutions. You need to find one x and one y. I can take this x solution and put it back into equation 3, so I can solve for the equivalent y value. This means that the x value of 71 over 21 and the y value of 19 over 21 will both simultaneously solve both these questions. Right, if I have to look at it from a graphical standpoint, hope you would understand this. We have both these equations. If you graph it on a graphing calculator, we have two equations that will give us two graphs, and at that point where they both intersect will be that value, that common x and that common y value. So it'll satisfy both equations. It'll satisfy both equations or both functions simultaneously. That's the reason we're trying to find the point of intersection, is what we say when we're trying to solve the system of linear equations. But this is only true if you're finding when you have one solution, right? If you have no solution, mean that they are parallel, so that means that they will never intersect, right? And if you have infinitely many solutions, mean that they overlap. They sit directly one on top of the other. But that's done at university. Okay, so that's how we solve when you have one solution. Now let's do an example when you have no solution. Let's say you're given 2x plus y is equal to 4 and 2x plus y is equal to 2. So now you have two equations, you have two unknowns. So we have a system. So now we can solve. I have to write either one of the equations with one of the variables being the subject of the formula. So let's say I take a variable from equation 1 and I make it the subject of the formula. Then I can take that variable and substitute it into equation 2 so that I can get it as an equation with a single variable, so we can use the linear equation techniques to solve, like the BODMAS and the additive inverse and the multiplicative inverse. So we will rewrite equation 1 in a form so that we can be substituted into equation 2. We choose variable y since it will avoid the use of fractions. So if I look at equation 1, y is equal to, if I subtract by 2x on both sides, I'll get y is equal to 4 minus 2x. This 4 minus 2x can get substituted back into equation 2. So that will leave me with 2x plus 4 minus 2x is equal to 2, right? If I substitute this equation 3 back into equation 2. So therefore this will leave me with 2x plus 4 minus 2x is equal to 2. The 2x and the 2x are cancelled, so therefore we're saying 4 is equal to 2. But we know logically that 4 cannot be equal to 2. So that's what you need to write. 4 cannot be equal to 2. So therefore what we're saying is we have no solution. From this we can see that there's no solution. Let's see how this would look graphically. So if I look at this here, you can see that both these functions when sketched, they are parallel to each other, meaning that they are equidistant. They have the same distance. So therefore they will never intersect. So therefore there'll never be a solution that is common to both functions or both equations. Now, what I wrote here is something that you can only understand after we do functions. Like I said, I will come back to this and I will explain all of this after I've done functions with you. Right, so just leave that for now. So far we've done substitution and I've showed you how it looks when you're given a scenario when you have one solution and you're given the scenario when you have no solution. Now let's move on to elimination and I'll solve these exact same questions and see how the technique differs. Okay, let's do that now.